Welcome everyone. Today I'll be giving a talk on a four-third approximation algorithm for the minimum two-edge connected multi-subgraph problem in the half-integral case. This is joint work with Sylvia Boyd from U Ottawa, Joseph Cherian, Robert Cummings, Logan Kraut, and Lou Wong from U Waterloo, and Zoltan Siketi from Grenoble in France. Let me start with the two-edge connected multi-subgraph problem, which we call 2ECM. We are given an undirected graph, G bar on n vertices, and non-negative edge cost C. Our goal is to find a two-edge connected spanning multi-subgraph H of minimum cost. Here, spanning means the subgraph should span all vertices, and multi-subgraph means that we are allowed to use more than one copy of an edge. The cost of H should also account for multiplicity of the edges taken. Because we are allowed to have multiple edges, we can, without loss of generality, assume that G bar is complete and that C is a metric. What it means is that C satisfies triangle inequality. Here's a small example which shows an instance of this problem and two feasible solutions for this. Some quick remarks about 2ECM. This problem is NP-hard. It's also very closely related to a very popular problem called as the traveling salesman problem. TSP is simply 2ECM plus the restriction that the solution have Eulerian property. What this means is that we want even degree at vertices. Since the problem is NP-hard, we want to design approximation algorithms for it. Here's the integer linear program for 2ECM. It's a very natural program. The constraints x of delta s at least 2 stipulates that the edge connectivity be at least 2. XC denotes the number of copies of edge E that we want to include in our solution. And we require that XC be integral. Relaxing this program gives us a lower bound on the optimal solution cost for 2ECM. Here's the linear relaxation for this problem. Observe that we also have additional constraints which say that the fractional degree should be exactly 2. We can add such constraints without increasing the LP value thanks to the parsimonious property due to Goemans and Burt-Simage. Observe that adding fractional degree constraints turns this LP into a very well-known LP called as the subtour LP for TSP. This is the reason why I said before that TSP and 2ECM are closely related. Here on, I'll use 2ECM LP and subtour LP interchangeably. I'll use script P to denote this polytope. LP opt denotes the minimum cost fractional solution in this polytope. The famous polyhedral analysis of Christofides' algorithm shows that the optimal solution for TSP is upper bounded by 3/2 times the LP optimum. Opt for TSP is at least as large as the opt for 2ECM because 2ECM requires a less restrictive solution. In other words, the integrality gap alpha 2ECM is at most the integrality gap for TSP, and this is at most 3/2. In the title, we mentioned half-integral instances. An instance is called half-integral if the fractional LP relaxation, if the LP relaxation is optimized by X such that 2 times X is integral. Half-integral instances can be seen as half-integral solutions can be seen as the simplest non-trivial fractional solutions because they have the smallest non-trivial denominator. Another reason why such instances are studied is due to a conjecture by Schallekamp, Williamson, and Van Zyl. They conjecture that the integrality gap of subtotal P is attained on half-integral instances. What's known for such instances? More than 2 decades ago, Parr and Ravi showed that the integrality gap of 2 ECM on half-integral instances is at most 4/3. They show that the uniform vector 4/3 X dominates a convex combination of 2H connected multisubgraphs. The result is constructive, but not polytime. And our work focuses on designing a polytime algorithm for this result. Recently, Carlin Klein and O.H. Garan showed that the integrality gap for TSP on half-integral solutions is strictly bounded away from 3/2. In fact, they give a randomized approximation algorithm for it. Our main result is shown in Theorem 1. Given an instance of a half-integral instance, given a half-integral instance and an optimal half-integral solution X, in order n squared time, we can compute a 2H connected spanning multisubgraph of G bar with cost at most 4/3 C transpose X. We can actually strengthen this result even more by using the meta-rounding algorithm of Parr and Wempala. We can use the above 4/3 approximation algorithm as a black box and obtain a convex combination of 2H connected multisubgraphs that is dominated by 4/3 X. To prove Theorem 1, we'll be reducing our problem to a different problem. And to make this reduction, for this reduction to work, we'll be working with a different graph. We consider the graph induced by this half-integral solution X. Basically, G is just 2 times X. Intuitively, that's what it's trying to model. The vertex set for G is the same as V bar, and capital E has exactly 2 times XE copies of HE. If we consider the half-integral solution, which is shown here, then the graph induced by 2 times X is shown here. Every half edge gives rise to exactly 1 edge, and 1 edges give rise to 2 parallel edges. We use the same cost function that was there in the original graph for the cost on the edges in this graph. Parallel edges basically get the same cost. Since the fractional degree is exactly 2, it is easy to see that G is 4 regular. Since X of delta S is at least 2, we can see that G is 4H connected. Here is the reduction. Finding a 2H connected solution in G bar of cost at most 4/3 C transpose X reduces to finding a 2H connected solution in G of cost at most 2/3 the cost of G. Here, the factor 2 difference that you see is because cost of G is simply 2 times C transpose X. Here on, we'll not focus on the version of 2 ECM and rather like focus our attention on trying to find cheap subgraphs of 4 regular 4H connected graphs. Here's a theorem from Parr and Ravi's paper. Given a 4 regular 4H connected graph G and an arbitrary edge E, there exists a convex combination of 2H connected spanning subgraphs of G minus E, such that this convex combination equals the almost uniform vector shown here. Observe that I have highlighted subgraphs in green. The reason for this is because it's a strict subgraph. The subgraphs HI use at most 1 copy of an edge in G minus E. However, HIs can have multi-edges as long as they come from distinct multi-edges in G. Our result builds upon the result of Parr and Ravi. So it is a good idea to just see a quick proof of like what they do, just the high level idea. So we want to express this uniform vector as a convex combination of two edge-connected subgraphs of a regular 4-edge-connected graph G. Parr and Ravi's proof is inductive, and it has two cases. In the first case, they consider case 1 happens when E belongs to a non-trivial tight cut. It's shown in this figure. You have 3 other edges, and E crosses this cut. Observe that you can obtain 2 smaller instances of the problem by contracting each of these shores, and then recursively solving these problems. You can also see that it is easy to lift the solution back to the original graph simply because the total mass crossing the cut is exactly 2. And because we are working with 2 edge-connected subgraphs, there is always a consistent way of gluing solutions that come from each of the smaller subinstances. Case 2 happens when case 1 does not apply. That is, for all non-trivial cuts that contain the edge E, there are at least 5 other edges. This case is complicated, and since this is subsumed by our analysis, we'll cover the details later on. Here are some high-level simplifications of Parr-Ravi's proof that we give. First of all, we get rid of the gluing step. This unifies the analysis and also gives us a very natural way of de-randomizing our algorithm. We handle all remaining cases by an extension of Lowasch's splitting off theorem, and this is due to Bang-Jensen et al. Theorem 3 is due to us. What we show is that given a regular 4-edge connected multigraph G and an arbitrary edge E and arbitrary edge cos C, observe that we allow the cost to also be negative. Then in order n squared time, we can find a 2-edge connected spanning subgraph H, which excludes the edge E, and the cost of H is within 2/3 the cost of G minus E. Again, note that it is a subgraph. What this means is that each edge in H appears at most once, and we use at most one copy of an edge in G in H. To understand our proof, we need a few basic definitions. We'll now see 3 definitions, which will lead to a technical lemma, and then we are ready to work through the proof. We define the splitting off operation now. So given a multigraph G and 2 edges SV and VT that share an endpoint V, the graph GST that is obtained by splitting off this pair of edges at V is given by G plus ST minus SV minus VT. What this means is that we delete the edges SV and VT and add the edge ST. It's shown in this figure. The next definition concerns complete splitting. A complete splitting at V is a sequence of splitting off operations at V until the degree of V becomes 0. So we have a graph G and a vertex V with even degree. A complete splitting is a sequence of degree of V over 2 splitting off operations at V. Here I've shown a complete splitting at V, in which the first operation is splitting off at SV and VT, and followed by splitting off PV and VQ. This is the residual graph that you obtain. Since the degree of V becomes 0, it is customary to drop this vertex. the last definition is that of an admissible pair, we use the symbol lambda to denote the size of a minimum cut. Suppose that we have a graph G on the vertex set capital V plus little v. V is a special vertex. Suppose that for all non-special vertices, the edge connectivity is at least k. Let SV and VT be two edges which are incident to V. We say that this pair of edges is admissible if performing a splitting off operation at these edges still preserves global edge connectivity for all non-special vertices. Furthermore, we also define AE to be the set of admissible partners of the edge E. That is, as long as E and F form an admissible pair, F belongs to AE. Let's see a quick example just for clarification. In this graph, E is the special vertex, E is the special edge, and we are interested in determining the admissible partners of E. It is easy to verify that splitting of SV and VT still maintains 4-edge connectivity. And the same result holds if you split off SV and VQ. On the other hand, if you tried splitting off SV and VP, you can see that the residual graph has a 2-edge cut, which is shown here. Therefore, this pair of edges does not form an admissible pair. Here's our technical lemma. This can be seen as a special case of the lemma from Bang-Jensen et al. Given a regular 4-edge connected graph and an arbitrary edge that is incident to V, this particular edge has at least 2 admissible partners. Basically, what this means is that this edge E having two admissible partners was not just a coincidence. This is always true. Furthermore, if E and F form an admissible pair, then the remaining 2 edges in delta V, they form an admissible pair. This is trivial to see because once you perform a splitting off on an admissible pair, then the residual degree of V is 2. And it is easy to see that whenever you have a degree 2 vertex, just ignoring it, just forgetting the label of that vertex still preserves global edge connectivity. We're now ready to give a simpler proof of Carr and Ravi's result. Recall that we want a convex combination for this uniform vector. We proceed by induction. The base case is trivial. The base case happens when you just have 2 vertices connected by 4 parallel edges. It is very easy to produce the desired convex combination. To give a proof of the general case, why an example? Consider the same graph that we saw before. The edge that we want to exclude is highlighted in pink. It's UV. By the technical lemma, we know that it has at least 2 admissible partners. In this case, it is Vx and Vy. This gives rise to 2 distinct complete splitting off operations for us. The first one can be done by splitting off UV with Vx, followed by ZV with Vy. This gives rise to the instance G1, which is shown on left. We have 2 new edges that were previously not present in the graph, and observe that all the edges incident to V have been deleted now. Similarly, we can obtain another instance G2 by splitting off at UV and Vy, followed by ZV and Vx. This gives us the graph G2. The partner of UV whatever is the splitting of operation, it gives rise to a dummy edge, a new dummy edge. We'll designate that as the excluded edge for our sub-instances that we create. We get two smaller instances on n-1 vertices each. Inductively, we can obtain convex combinations for each of these sub-instances. Observe that the convex combination that we get here is precisely 2/3 chi of E minus delta V plus YZ. The edge UX does not appear in the convex combination, simply because it's excluded. Similarly, we have something for G2. So we have obtained convex combinations of two edge connected subgraphs of G1 that correspond to this vector. How can we translate it back to the original graph? Observe that G1 and G are almost similar, except for this particular dummy edge, the green dummy edge. So if we have a subgraph, which is a subgraph of G1 that uses the edge YZ, if we want to translate it back to the graph G, then we need to figure out a way to replace that edge with edges from the original graph. So this process is called as lifting. So we need to translate our solutions, the inductive solutions, back to the original graph. We define the lift operation for G1. Given any two edge connected subgraph H of G1, the lift of H is defined as follows. If the dummy edge YZ belongs to the subgraph, then we subdivide it at the vertex V. If the edge does not belong, if YZ does not belong to H, then we simply add these two edges, Vx and Vy, to the graph. Recall that we have a convex combination for this vector, which is shown here. If we apply the lifting procedure to each of the constituents of this convex combination, then we get this vector. The explanation for this is as follows. Observe that the dummy edge YZ belongs to the convex combination 2/3 of the times. So whenever that happens, you get a weight of 2/3 here and 2/3 here. And the dummy edge does not belong with probability with weight 1/3. So in that case, we get 1/3 mass on Vy and 1/3 mass on Vx. Overall, Vy is always present and Vx is underrepresented. So the convex combination that is generated from the left subinstance is a bit skewed, like it's almost uniform, but with a small amount of skew. Fortunately, performing the same lifting operation on the graph G2 in a symmetric way ends up producing another convex combination which is skewed. And the nice thing is that these skews cancel each other. Taking a simple average of these convex combinations gives the desired convex combination for the graph G. This finishes the proof of Theorem 2. We now focus on the algorithmic version of Theorem 2, which is Theorem 3. We want to compute a cheap subgraph, two edge connected subgraph H of G minus E in order and square time. We won't focus on the runtime in this talk. We'll just give a polytime algorithm. Observe that the naive algorithm, which recurses on both branches, is too expensive. In each recursion, we only drop one of the vertices. So this algorithm, this naive algorithm, is going to take at least exponential time. Our main idea is to recurse on the cheaper branch. Basically, we are just using the method of conditional expectation. Recall that the convex combinations that were produced from the left and right subinstances are shown here. If we were to be greedy in making a decision, then it is easy to see that if Vx is the more expensive edge, then we should recurse on G1 because Vy is overrepresented in that convex combination. Similarly, if Vx is the cheaper edge, then we should recurse on G2 because Vx is overrepresented in the convex combination obtained from G2. That's our algorithm. Without loss of generality, we assume that Vx is the more expensive edge. So we are recursing on G1 with the excluded edge Ux and the dummy edge Yz shown here. A valid instance of the problem also requires that we define an edge cost on Yz. For now, we'll treat it as a variable. We'll soon give it some value. Let H be the recursive solution that we obtain by running the algorithm on G1 with the excluded edge Ux. We get a subgraph H whose cost is at most 2/3 the cost of G1 minus Ux. Simplifying it gives us this expression. Now observe that based on what this recursive solution is, translating it back to the original graph can lead to two different outcomes. If the dummy edge belongs to the subgraph, then we subdivide it at B, same as what we did in the existence proof. And if the dummy edge does not belong to H, then we include the edges Vx and Vy. Observe that the edge Vy is always present, whereas depending on what outcome comes out, we do two different operations. If we look at the increase in cost from H to the left of H, then it is easy to see that in the first case, it is the cost of Vy plus the cost of Vz minus the cost of Yz. Whatever we paid for Yz is reimbursed to us. And in the second case, the increase in cost is cost of Vy plus the cost of Vx. Since we cannot be sure about which edge is included in the solution, whether or not the dummy edge is included in the solution, we have to be prepared to pay for the worst case increase. So the cost of lift of H can be bounded by this quantity. If we set the cost of the dummy edge Yz to be cost of Vz minus the cost of Vx, then it minimizes the increase in cost. Basically, it is a balancing act. We ensure that both these quantities are the same by this choice of cost. It is possible that the cost of Yz becomes negative now, but this is okay because I mentioned earlier that the statement of Theorem 3 allows arbitrary edge cost. Overall, the cost of lift of H is upper bounded by the budget that we had, plus 1/3 the difference between the cost of Vy and Vx. And because Vx is the more expensive edge, lift of H is the desired subgraph. This finishes the proof of Theorem 3. Now conclude my talk with a summary of what we saw. We saw a simpler proof of Parr and Ravi's result, which says that the integrality gap of 2 ECM on half integral instances is at most 4/3. We also gave a matching approximation algorithm for this result. What we know so far on this integrality gap for 2 ECM on half integral instances is that it's lower bounded by 6/5 and it's upper bounded by 4/3. This naturally leads to the following three questions in increasing level of difficulty. The first is, are the integrality gaps for TSP and 2 ECM, is there a gap between these two numbers? The second question is the integrality gap of 2 ECM for half integral instances strictly bounded away from 4/3? And the hardest of questions is the integrality gap of 2 ECM on half integral instances exactly 6/5? With this, I conclude my talk. Thank you for your attention.